this computer. Okay. All right, so we'll start. So welcome to Emil's first workshop of the semester. We're gonna be learning how to use neural networks in PyTorch, and we're gonna be dealing with the most basic version of the neural network. Okay. Right, so neural networks, where does that name come from? Well, neural networks are a machine learning technique, and they're really inspired by the human brain. So what happened a couple of years ago is that people found out that brains were made of neurons, and they were like, holy crap, this is a very cool sort of idea. Maybe we can implement this, and maybe we can artificially make this stuff happen, and through mathematical laws and stuff, and then sort of have it learn things like we do. So the basic structure of a neuron, so in a human neuron, you've got connections between neurons and stuff. So this here is called a single layer perceptron, or a single perceptron. So this guy here is your perceptron. Now that's also known as like a node, or an output node in this case. And so what it's supposed to do, or what it's composed of, or what the whole network is doing, is you've got these input layer, or these inputs that go into the output, and you've got this little function in here that computes what happens with the inputs. So it takes all the inputs and then does something with it, and then produces an output. Now these weights in the middle, right, they're supposed to be things that you can change, right? So the inputs you can't change. The output can only be, I guess, manipulated or changed by the weights. Now, if you think back to human brains and human biology, you'll notice that people say the phrase neural pathways, right? That's the thing that gets strengthened over time when you practice, I don't know, playing the violin or playing the piano. You slowly over time develop neural pathways, or strengthen specific pathways, which then make you better at things. Now, the whole goal in a neural network is to strengthen these weights, is to identify which weight actually makes the connection stronger. Now, activation functions, buzzword, not really. So activation functions are the ones that decide whether the neuron fires or not. Now, going back to the example of human brains, whenever like you're like the neurons in your brain make the decision of whether to fire or not. But it's not a binary decision. It's a probabilistic decision. So it's between 0 and 1. We try to simulate that in neural networks as well. So we've got a whole heap of these kinds of these functions. We've got the sigmoid function, we've got the softmax, we've got tanh, and one called ReLU, or rectified linear. Now, if you see, both the sigmoid and softmax look almost the same, but they're not. The way they're computed is different, and they have different use cases. Same with the tan function. Now, the difference between sigmoid, softmax, and tan is that the sigmoid and softmax go from 0 to 1, whereas the tan goes from -1 to 1. So there's different use cases here. And then rectified linear is basically your typical max 0x function. It's 0 until you get into the positive integers or positive numbers, and then it starts climbing like a normal linear function. And those are used in like what's called hidden layers. Okay, so, well, that's too much stuff. Let's go back and look at just a single layer of input and output nodes. Now, as we discussed before, we've got input neurons, we've got weights, and we've got output neurons. Now, the inputs are all the things that we observe. right? So if we're dealing with images, then typically we tend to pick an input neuron for every pixel value in the image. And all these neurons, each one of the neurons is connected to an output one, and each connection has a specific weight. Now, if we assume, say, this is like you're trying to pick whether one is a cat, dog, or bread, for example, what's going to happen is every time it actually, you know what, that's the next thing, sorry. So how do they work, right? We can see that everything, you know, you've got input, outputs, you've got weights, but how does it all fit together? So there's this technique called back-propagation. Now, the problem with this thing is there's too much math involved. It's very calculus heavy. And so when we don't have enough time to go through it, so we'll skip the math, but we'll go through the intuition. So it's a method of gradient descent. Now, if you've been to one of our other workshops last semester, we did talk about gradient descent, but I'll briefly go through it again today. So backpropagation has 4 steps. The first thing you do is you compute the error of the outputs, right? So when you make an output, you want to compute all the, so for example, the network predicted dog, but the actual image was a cat, right? So then there's an error, right? That's wrong. So now you want to tell the thing that it's gone wrong. So what you do then is you calculate the error at the output, and then you calculate the error of all the subsequent layers. And then you update all the layers as you go. It's easier to say than actually do it, but a very beautiful visualization of this. So now we've computed our output, right? And then every time it goes back, it's updating the weights. And at the end of the thing, you can see how some of these lines are highlighted more than others. The highlighted lines means those pathways are strongest for that particular. So in this case, this neural network is trying to predict that 5 equals 5. The handwritten digit 5 equals the actual digit 5. And so I guess another visualization of this is you're calculating everything. You got the error, and then you derive. So the calculus is, you know, chain rules. So there's a lot of chain rule derivation involved when you're trying to do back propagation. Once again, it's easier to say than actually do it. There's a lot of steps, especially when you have a lot of layers and things involved. Right, so gradient descent, the whole, I guess the master, the bigger picture of gradient descent, or what the neural network is trying to do, is from a high point, you want to get to a local minimum, right? So you want to get to a point where it's at the minimum, at a point where you have higher accuracy and less or lower error rate. So I guess in a way, if you want to visualize this in a different way, so every time you make a mistake here and you update the weights, the pathway gets stronger, or like in this case, more highlighted. And so that just means the weights get bigger on some pathways than other pathways. And yeah, that's pretty much all there is to a neural network in terms of high level understanding. Yeah, any questions on theory, or do you guys want to get started? All good?
All good, sweet.
Okay. So, can everybody see that, or should I zoom in, or
Just zoom in a bit.
zoom in a bit? Okay.
Should be fine.
All right. So here we have, so we're using the framework called PyTorch, a very popular framework. I'm pretty sure it's developed by Facebook, right?
Yep.
Yeah, developed by Facebook. So yeah, so if you haven't downloaded it yet, and you're on Python, it's just torch and torch vision. That's the command if you have to download it. I'll just put that in the chat. Anyway, so we're going to use a data set called the MNIST dataset, and that's a very large data set of handwritten digits. And so it's all been labeled for us. It's everything's done. So the only thing you have to do is actually create the model and train it. I'll let my colleague explain this stuff because he wrote this file.
Can I just get access?
Yeah.
All right, sweet. So let's just start by defining what a data set and a data loader is. So data set is just a class which holds your image and its label together. And then a data loader just gives you the value of the image when you call it. So just for an example, so for here, we just run this and then we're just downloading the data.
It's done. I already have it downloaded.
Oh, it's done. Yeah. Sweet. Now we'll just define a data loader. So it's just going to give us images and their labels. Batch size means how many images are we getting each time. So in this case, we'll get 64 images and 64 labels. Yep. So we're just going to go over the data loader and get our X and Y, which I'm running them again. Yeah. Scroll. Yeah, cool. So just an example. This is what we get for one of our images. Yeah, so you can see the shape of the tensor that we get.
Do you want me to? Wait, just give me a second.
Yeah, I can't scroll it for some reason. Yeah, we'll just use this.
Okay, wait, just give me a second. Wait, stop. Let me just change my. No, I need to stop sharing. Hello. Okay. Nope. Can you let go of the mouse for a second?
Yeah.
Okay, can you scroll? Like, is that?
Oh, can you just scroll then?
I'll scroll for you, just talk. Yeah, that's better.
Right, so right here, this is just an example of what we get. So we get a number, which is an 8, and then the label for that image, which is a tensor, with the value 8. So in this case, we just have 10 classes, one for each digit. So that's 0 to 9. And then scroll down. So this is what our model is, just as we discussed multi-layer perceptron. So we've got a 28 by 28 input layer because our image is 28 pixels by 28 pixels. So our number of pixels is 28 by 28 multiplied by 28. Then we have 5 and 2, an activation function. And then 2 more layers. And then in the last layer, you can see that the output is 10 neurons because we've got 10 digits that we want to find out. So we'll have the probabilities for each digit in each neuron. Then we define the forward method, which is just how our data is going to travel. Yeah.
So the forward method is, if you remember this GIF, is what happens when you see the things going forward. That's the forward method. Yeah. Okay.
Right. This is just showing how the model works. So we input 28 by 28 single channel image because it's a black and white image, and then 1. So that's one image, so one channel, 28 by 28 pixels. Yeah, and then the output that we get is 3 in this case. It's a random image. So yeah, like there's no logic.
This is just testing to see if the model is actually configured properly. So that there's like no errors or Python doesn't complain about things. So this is not actually doing anything other than just testing.
You want to go over the training loop, Arvind, just showing how it's working with the slides?
Sure.
Just like the back-propagation part and stuff.
Yeah. So with the training loop, so you can, okay, so first of all, this thing is sort of important. so we've got a learning rate, and that's the step we take. So down here, if you look at this, so you see how these lines, the length of the lines, that's the size of our step. Now, obviously, this is in 3 dimensions. Typically, these problems, for example, this particular one is happening in, I think it's 28 by 28 dimensions.
Yeah.
Yeah, so it's a very large dimension, and so you can't really visualize that properly. But so the learning rate is just the size of our steps that we take to get closer. Now, epochs is up here. So it's just the number of times we iterate over our data set. The reason we do this is because we want to show or like teach the neuron the layers and configure the weights automatically. So like we just want to show it what a 5 is a multiple, like a couple times. Like when you're learning to write, right? You don't learn how to write the first time you write. You learn how to write after you write a word maybe like 20 times or 30 times, right? So that's basically what this is doing. We're teaching it how to recognize digits by showing it to it over, like showing the digits to the model over and over again so that it picks up and strengthens the weights over time. The loss function, that's just the thing to calculate the error. Optimizer, that's the, I guess, the thing that, actually, Ariman, I think you can explain this better than
You
me.
just want to, we can say, so we've seen gradient descent. So this is just a variation of gradient descent.
Yeah.
Adam, we can use gradient descent as well, but
Yeah.
Adam is faster than gradient descent.
Yeah.
That's
Okay.
pretty much all it is.
And this thing is, I guess, the most important thing of all machine learning enthusiasts, the device that you use. If you have a GPU, always stick to using a GPU because it does things way faster than what your CPU can do. I have a dedicated graphics card, so I will be using that. Okay, so training loop. So in, like, just keep that GIF in your mind, or GIF if you like, and let's go through this. So what's happening here is we're saying, okay, let's convert all of these numbers that we've given into the type that the device accepts. So GPUs and CPUs don't really accept the same type of, like, I guess, bytes. They have different structures and different data, what do you call, data structures. And so we're just doing the conversion here before we hand it off to the GPU. This is prediction. So this is the forward pass. So we're going through, okay, input, hidden layer, and then we're going through the output and we're getting the prediction. And the prediction is usually a set of probabilities for all of the numbers. So unlike us, when we look at digits, we don't just say, okay, that's always going to be that's a 3, that's a 4. We don't say definitively. We give a, like, our brain pulls up a probability distribution between the numbers, and then we pick the maximum of those. So in your head you might be like, oh, that might be a 4, that might be a 6, but when you say it out loud, it's definite. That's because you picked the maximum. And so it's going to output a list of 10 numbers, or a tensor in this case, a tensor of 10 numbers. And we're just calculating the loss, so the difference between the actual and the predicted. And then this is the back propagation. So remember those steps for back propagation. We calculate the losses. We've done that already, and now we're just going through and doing the other steps. So updating all the weights by doing differentiation. And then we're taking a step in the correct direction. And this is just how he outputs the thing. Test loop is just testing the model. So every time we train it for an epoch, we want to test its accuracy. And we're going to display the improvement in accuracy over time.
Yep. So we test on a data set that the model's not seen before.
Yeah. So that's important. The model
That's
would not
just
have
another
seen it.
point. Yeah.
Yeah. So it's like when you do a math exam, right? Your teacher never gives you the same stuff you got for homework. You get a new set of problems. Okay. And then here we're just doing the training. So in the first, so up here we're doing it for 5, not 50. That's way too long. So basically what's happening is it's doing forward pass and then calculating gradient descent, doing forward pass, calculating gradient descent, and then we're doing accuracy calculations, and then we're doing the whole thing again. But every time we redo the epoch, we actually have to shuffle the database, the data. Otherwise, what's going to happen is it's going to pick a pattern and follow that pattern specifically. This is actually one of the problems with neural networks is they're very good. They're almost like humans in picking up patterns. They pick up patterns where there is none sometimes. So that's very important. Okay, so it seems we have achieved 97.2% accuracy and an average loss of 0.0946. This loss, the lower it is, the better. It's not exactly a percentage, but
so the loss is just how far your predicted probability is from the original class.
yeah,
That's what the loss represents, basically. So
yeah, okay. So now, earlier today, I did some drawing, or not exactly drawing, but I wrote some digits down. So I wrote an 8, a 5, 4, 9. I wrote the whole, like all of them. And so
are
what
you
we're gonna
showing the
do,
digits or we can't?
I'm not so, oh God, okay,
Oh.
sorry, I need to change this. Share my desktop. Okay, now you should be able to see it. Yeah, so I wrote down some digits and I snipped them. So these pictures are all by 100 pixels by 100 pixels. What we're gonna do now is we're just gonna go through this complicated line. Okay, so we have so Python has this library called OpenCV. It's, or for full form is just Open Computer Vision. It's one of the best libraries you can use for computer vision. It's open source, so it's amazing. And then we have this library called Pill, or Pillow as it's known, the name. And that's used for image, like to open an image and stuff. So the first thing we do is open the image using the function in Pillow called image. And then we convert it to a NumPy array. And then we convert the color of this image to grayscale, black and white, using OpenCV. And then we invert the color of the image. Now, if you notice the image, I wrote using black ink on a white piece of paper. But if we go up here, you can see that it's black on white, right? So you've written, sorry, it's white on black. It's a white digit on black background. That does make a difference. Your model picks up these pixel values. So when it picks up these pixel values, all these black pixels are read as 0, and all the white pixels are read as 1 or 255. So what happens if I pass it white pixels, sorry, the other way around, what's going to happen is it's going to assume all of this is the number and the 7 that's over there is just the background. Yeah, they're really smart. So that's sarcasm, by the way. Okay, so we're just going to run that. So now we have a dictionary of images. And then now here what we're doing is, so PyTorch doesn't really play nice with NumPy arrays, because NumPy arrays are designed to be run on the CPU. What PyTorch, when you're using a GPU, is going to do is it needs to convert everything to a tensor, a data structure called tensor. So that's what we're going to do here. We're going to convert everything to a tensor. And that's what this transform thing is doing. I'm sure you can elaborate more on that, or
Yeah, so tensors are basically, so it's basically the same thing as a NumPy array, just an n-dimensional array. But the thing with machine learning is, even with, if you go to TensorFlow as well, so
Yep.
the name TensorFlow is just the flow of tensors
Yeah.
in a network, if that makes sense.
Yeah.
So it's just another data structure that we use for machine learning stuff.
Yeah.
Yes.
And I guess I have to point out, this is only used for neural networks, right? If I'm not wrong. Tensors.
Tensors, now they use for, so if you're using PyTorch or TensorFlow,
Yep.
you you use tensors
Right.
just
But
because, yeah.
I mean, like for traditional non-neural network machine
Oh
learning,
yeah.
when
No,
you're
you
just
can use
doing,
NumPy arrays, that's fine. But
yeah, when you're doing like when you're using scikit-learn, for example, you can just
yeah,
use NumPy for those. Um, yeah. So yeah, so I made a dictionary called transformed images, and then we're going through all the images that I loaded, and we're transforming them. So the first thing you have to do is resize them, because the images I cropped out were 100 by 100, but the model only accepts 28 by 28. So that's the first thing we do. We do that. We resize the images to 28 by 28, and then we transform them or convert them to tensors. Ignore this. This is not needed. And then I have all the labels out here. And so what this is doing is it's just saying, okay, so first thing we're doing is we're converting it to a GPU tensor, or GPU compatible variable, and then we're predicting on it. So we're using the model that we made up here, the one that ran 5 epochs, and we use that to predict on the image, and then I just have a little if statement saying if the thing comes out correct, then we +1 on the correct, and if it's not correct, then well, nothing happens. It just prints out the real versus prediction. Now, okay, so
it's gone worse.
it's gotten worse. So I guess the first observation you can make from this is that MLPs are bad. Multi-layer perceptrons are very, very bad for image recognition, specifically. So
So with MLPs, we lose
a
all the
bit
data
complicated.
about
Yeah,
which pixels are related, like what
yeah,
pixels are next to each other.
yeah.
And
So if you want to, I guess, get a more elaborate, I guess, better explanation from, because I'm finding it hard to put it into words. There's this video series by 3 Blue 1 Brown on neural networks. The first video actually goes over a little bit of the why multi-layer perceptrons don't really work so well. So I would highly recommend you watch that video, and so you can get a better intuition for why it doesn't work. But the thing is, it doesn't work so well because so first thing, if you've noticed, we're fully connecting everything. There's the image, right? So a multi-layer perceptron connects all nodes to every other node. Now, that's not always necessary. That's usually just increasing computation, and it might also increase bias. Now, the other thing is just the image that I produced may not be in the proper format that it was expecting, right? So that could be an issue. Now, if you look up here, actually, I did make a little. So after the resize, you can see my images look, in my opinion, they're a lot neater than what the ImageNet dataset has. Or sorry, not ImageNet, MNIST. Like that's very pixelated, right? So mine is a bit more cleaner than what they've produced. So that could be another issue. It's just it just didn't train for that one specific type of data. So these are all like just big problems with multi-layer perceptrons, which is why they're not used very often for anything. But it is a good starting place to learn and understand neural networks. Yeah, I'm all done explaining stuff. Yeah, Jason put the video link in the chat, so I would highly recommend you watch that.
So
Yeah.
has anyone got any questions though?
Any questions? This was supposed to take a little longer. Questions? No questions? Yes,
Yeah,
no?
I do just have the one. I guess kind of a bit broad and vague, but where did you learn everything that you have learned so far in neural networks?
Okay, so
Interesting.
I'm gonna let Aryaman explain this because
No,
he's.
I guess it's different for both of us. I guess
Yeah.
you can go first.
Oh, I can go first.
Yeah.
Okay. So I personally did a course at uni called Comp 4702. I don't know if any of you have done it before.
I was planning on doing it next sem.
Okay.
Yeah, I'll let you keep on.
Yeah, so that's, I guess, my first exposure to this formally. But before that, I did a hackathon called Telstra Digital Health. Telstra's Digital Health hackathon back in 2020, sometime in November. And that's when I really because one of the problems, actually, I can show you the stuff I did. Right, so what this hackathon, or the problem that we were supposed to solve was that, so there's this data set of cancer images, benign and malignant, and we have a skin cancer, and we have to make a model that can help a dermatologist with like a second opinion for a dermatologist. So this is really my first exposure to neural networks. This is where, and the hackathon was a week long. So it was like the full week. I was just learning and just exploring everything. So yeah, that's how I got exposed to neural networks. And then after that, during the winter break this year, I was working on a project with the professor who does stuff on neural networks and stuff. So yeah.
So I formally got to learn about this stuff last year in this summer break. There was Summer of AI thing. I don't know if anyone's heard about it at uni. So yeah. So it was just like going over image recognition stuff. Yeah, because it was mostly people from UQ. Just over summer break, yeah.
Okay, gotcha. And I'm not 100% sure how hackathons work. Do they teach you this using Torch? Is it called Torch or
No.
Sorry?
So okay, if you go to the course, the Comp 4702, the ML course at uni at UQ, they teach you TensorFlow, or at least they did when I did it last semester. But the year before they used something else apparently. So they might be shifting over to PyTorch because PyTorch is easier to use, apparently. But we don't know. It really depends on what you want to do. For example, the hackathon that I did, they didn't tell me use Torch or use TensorFlow or use one of the other open source packages, frameworks. No, they didn't tell me anything. I just decided to use Torch.
Gotcha. Okay.
So how do you decide the number of nodes in each layer?
Oh, just go with any number.
Yeah.
you know the input and the output, but for the other layers you can just go with any number. That's fine.
So for the typical image recognition problem, the input layers always are usually the number of pixels in an image. And then the output layer is how many classes you have. How many layers is standard?
There's no standard.
There's no standard. No. You see, one thing, like a little joke that goes around the ML community is, if it's not doing well, or if it's not predicting it like well, or if you don't have a good accuracy, just chuck another layer in. It'll get better. So
Or
yeah,
worse.
or worse. Yeah, it might get worse. So there's no real like standard for how many layers. I guess try 1, 2, 3, 4, 5, just whatever number comes to your mind, the first thing. But what I would recommend before you start messing around with layers, because sometimes depending on your data set and the size of your data set, it could take hours to days to train this thing. Look up things that other people have done already. Maybe read some academic papers and then make the decision based on that. That's one way I would recommend doing it. Cool. Any questions, comments, concerns? All good?
And if anyone wants to like know about convolutional neural networks for like image recognition stuff, Arvind's doing a workshop next week.
Yep. So the brother, or the big brother, or I guess the next level to this on how to use the neural networks for image recognition specifically. So I think back in 2012, around that time, something called a convolutional neural network was developed. We'll go into more detail about this next week when we do. Is it next week? Yeah, it's next week. During the presentation. But what that really changed the game in terms of how image recognition and stuff works. So like right now, you're getting good accuracy on the test data, but when you actually have to put it into practice, it sucks, right? It thinks a 4 is a 3. It thinks a 2 is a 3. It thinks a 9 is like, I don't know why it thinks a 9 is 3. But yeah, so convolutional neural networks really are a very huge improvement on this area. Yeah, and that's next week.
Continuous output.
Yeah.
So wait.
What do you
there's a
mean
question.
continuous?
Yeah.
Instead of 10 discrete
Oh
categories.
yeah. So in this implementation, we don't actually have 10 categories per se. We just we find which category it belongs to based on what neuron has the highest probability. So I mean the output is continuous.
Okay, so I guess okay.
Or maybe you mean image to image. Yeah.
So just tell me if this is what your question is. Are you asking me if you can have a continuous because okay, so before I ask you what you mean, the output is the number of classes you have. So in this case, we have 10 classes, one for each digit. Okay. That has to be discrete because it's a class. Now, depending on your data set, you might have like a gray area, right? Nothing, damn, I can't think of a good example, but you can have like gray area between classes. Sometimes there might be one class being predicted as another. I don't know if that's what you consider continuous. So you're trying to predict something that isn't classes, say height. Well, you can't really. Predict.
I mean, you can, but so there's better approaches than
Yeah,
having a neural network.
yeah. Neural networks are not. You might want to try more traditional machine learning for that. Something like support vector machines, or actually regression works great for that stuff. If you have like a bunch of heights and you want to figure out the correlation between two variables, I'd say regression would be great. Probably like multi-dimensional regression should be all right. Yeah, there's so many machine learning techniques. Cool. Actually, I'm assuming all you guys are UQ students, right? If you are, there's this textbook. There you go. That's an Amazon link, but still. Right, so there's this textbook by this guy called Alpython, Introduction to Machine Learning, great textbook. If you're a UQ student or a university student, you should be able to have access to it from the UQ library. I would highly recommend you read it. It actually goes through a lot of the mathematical stuff involved in machine learning, gives you a good understanding of all that stuff. And there's another textbook. Yes, they do use that in 4702. Actually, they use a lot of textbooks in 4702 and a lot of papers. But that is one of the most important or highly used textbooks. The other one is this guy. This one goes through a lot of the mathematics behind neural networks. Like I said, there's a lot of math. We don't have enough time to go through it. But this textbook has an entire section dedicated to deriving the mathematical know-hows and background of neural networks and stuff. So I highly recommend you read it. I think it's chapter 4.6 or something in there. So if you want to have a read of it, would highly recommend. Great textbooks. Yeah. But yeah, one thing to keep in mind is this whole machine learning and neural network stuff is always evolving, and it's always like you have to keep up with the pace. So if you want to, I guess, learn more about this stuff, textbooks, academic papers, and doing stuff on your own is a fantastic idea. Most of the things you want to do, you can find data sets in Kaggle, right?
Oh yeah, we can just show Kaggle once.
Yeah.
You might want to try out Kaggle.
Kaggle. How do you spell it? There you go.
Yeah, that's it.
Kaggle. Great website for data science. So all these are data sets? No, they're not data sets. There you go. There's a data set for skin cancer. Now the beautiful thing about Kaggle is all the data is in a great format. And I'm pretty sure there's also a Python library called Kaggle that you can just use to download stuff.
Yeah.
Yeah. So Ariman can give a bit more information on Kaggle because he's currently doing a hackathon right now.
Yeah, so you've got like access to hackathons and stuff, and then you can also go into code, just go to code,
Yep.
and then you can find notebooks on like a lot of stuff. Just even if you search for a MLP notebook, I'm pretty sure. I mean, yeah, there's like a lot of stuff.
Yeah, so this guy's just done some cool PyTorch stuff. Yeah, so
Yeah, and if
the
you want
question.
to
Sorry,
try
go ahead.
stuff out, go to competitions and
Yeah.
so that's, yes, these are like sample ones, but then if you scroll down, there's like some big money competitions on the
Yeah.
website. You might want to try them.
Yeah, and the best way to learn machine learning is to actually learn. Like, all good. See you, Tanvi. But yeah, so get your hands dirty. Just, I mean, if you have a laptop like a Mac or something that doesn't have a dedicated GPU, you're a university student. Use the resources at your university. If you're an EAIT student, you have access to the Goliath cluster. Just use that. Ask a friend, or I think we can probably go through that at some point, or send a message to one of us. I think we have used Goliath before, so we should be able to help.
Yeah.
Um, or there's a computer lab in GP South. Sorry,
Yeah, but
General.
that's restricted though. So.
But EAIT.
But you can get in though.
You can get it. Just knock on the door. People allow you in. Log into a computer. There's usually PyTorch and TensorFlow are installed on those things. But if they're not, figure out how to install it, and then just work on it. So yeah, I mean, just because you have a MacBook doesn't mean you can't do it. I know I'm throwing shade at Macs, but this is to all computers that don't have dedicated GPUs. But yeah, like, don't be afraid to just get your hands dirty. Kaggle is a good place to find data sets. If you one of the, I guess, the biggest problems with this whole machine learning thing is data sets. My winter project, most of my time was spent in creating a data set for the problem that we were trying to solve. So, like, if there was a data set readily available, I probably would have used it, but there weren't any. So I had to create a data set, and most of my time went for that. So yeah, so you got Kaggle, you've got TensorFlow, you got PyTorch, you've got UQ's clusters. Or I mean, if you don't have access to UQ clusters, you've always got Amazon's AWS cloud. That's another great thing. Pretty sure you get free credit if you use.
Yeah, you can. If you use your student email, you can.
There you go. Use your student email, you get free credit. Easy peasy. Run some jobs on it. I actually used it for one of the hackathons we did last year.
Oh, just use Colab.
Oh yeah, Colab. We didn't do that. Just Google something called Colab. Not Lobe Lab. I'm not using Google. So go into Google and type in Colab, and you get to this thing called Google's Colab or Laboratory, and you can make your own notebooks here. And this is basically an almost this same implementation of Jupyter Notebook. So if you know how to use Jupyter Notebooks, you'll be at home with this. So yeah, just you can make a new notebook on here, give it whatever, just some random name, and I think you have like a limit of like 20 gigs or something for data sets, right?
Oh yeah, and if you want to use a Kaggle dataset, you can just start a notebook on Kaggle.
Yeah.
And that like import data sets and stuff for you. So
yeah, so that's another thing. And I guess if you want to play around with sample data on Google Colab, you've got like all these other MNIST and California housing and all these data sets readily available on Colab. And this thing says I have up to 70 gigs available. Not sure why, but different people have different amounts, allocations. And these things usually have a GPU in them, so you can just use the GPU to train stuff. But the only problem is you do get timeouts. So make sure whatever you're trying to train doesn't take like a day. Otherwise, you'll get timed out from the Colab. Well, at least that's happened to me. I'm not sure if that's not supposed to happen. But yeah, 10 minutes left. Any questions, comments, concerns? Thanks. All right. See you,
Awesome.
Miles. Have a good night.
Thank you.
Thanks. Thanks for coming.
Yeah, I was gonna ask, where's Alan gone?
Alan?
Alan, yeah.
Oh, exec Alan. I don't think he showed up today.
Yeah, Alan's not here.
Okay. Yeah, he was the one that I don't know. He was my tutor last sem, the
Oh.
IMS, and I told him like interested in AI, well, like machine learning. He's like, well, I know something about that actually. Yeah.
Nice.
Okay. Good stuff. All right. See you around.
All right. See ya.
Thanks,
Yeah.
guys.
Well, goodbye.
Okay, we're gonna stop the recording now.
Yes.
So we'll only upload like the presentation